All right, the central limit theorem. This one's the biggie, and it's important. It's important making in my opinion, making probably at least 2 videos on it because it's saying something quite profound and important to understand. My videos typically take more of a deeper understanding, as my title suggests. So as the author, I try to live up to my titles. So rather than going through sort of like standard plug-and-play kind of examples, I like to sort of talk about kind of what's going on behind the scenes. So that's what I'm going to attempt to do. Sampling distributions of the mean, very important concept used in the central limit theorem. I like to call them frequency distributions of sample means because that's really what they are. So let's start. What is the central limit theorem saying? In essence, it's saying that as your sample size gets larger, the sampling distribution, or the frequency distribution of those sample means, approaches a normal distribution with a mean of mu and a variance of sigma squared over n. Well, what's mu and sigma squared over n? Well, mu is your population mean. That's the mean that you're pulling your samples from. Sigma squared is the variance from that population. So you can see that the sampling distributions of the means has the same mean as the population, and it has a function of the original variance. So the beauty of the central limit theorem is that no matter what the distribution of your original x's, no matter what your distribution of your population, the distribution of the sample means always approach this. It approaches normality. It approaches a normal curve with those parameters. Okay. Now, one stipulation: we can't have an infinite variance. We can't have distributions that have variances that go into infinity. You're generally not going to be exposed to those, so you don't have to really worry about them per se unless you go on to more advanced statistics courses, in which case you probably will be exposed to them. But for the sake of demonstration, it's pretty much the case that the regular distributions that you're going to be dealing with will always converge to a normal distribution. These frequency distributions of the sample means will. So I like to always start with a uniform 0-1 distribution because it's easy to draw and it's easy to think of, and it's easy to appreciate the central limit theorem in action. So what are our parameters that we're dealing with here? We have a mu of 1/2. I'm hoping that's somewhat obvious. We got a symmetrical distribution where our mean's down the middle. We have a variance of 1/12. That's not very intuitive, but it is the known variance for this. So that's the population we're going to be pulling samples from. So let's take it from the top, as they say, and see what's going on with this theorem. Let's take a sample of size 2. So we take 2 random observations, and we get a mean. I'm going to call it, say, x bar 1. Let's don't confuse this x1 with this x1. Right? That's the mean of the sample. Okay, and take another sample of size 2. Say call that x3 and x4. And we get to the mean, and we just keep doing this over and over again to infinity, in theory, of course. These are theoretical distributions. We're not actually doing these. They're to show you what's going on. So the $64,000 question is, how are these means distributing? How are these individual x bars distributing themselves in a frequency distribution? What do they look like? Well, we can answer that. We have the technology, and in this particular case, for a uniform 0-1, it would look like this. It would look triangular. And since our parent population was bound on 0-1, all of our sampling distributions are going to be bound there too. But important to note that what are our parameters for this sampling distribution? Well, our x bar, or excuse me, our mu x bar. It's typically written as mu x bar, not to be confused with the original mu, of course, is the same as the parent mean, right? That's what it's saying here. Right? We have the same mean as the parent here, and it has a sigma squared x bar of, in this case, 1/12 divided by the sample size, by 2. Okay, so now again, the central limit theorem is saying that we're approaching the normal curve. Well, starting out with a sample of size 2, is that very normal? No, but if we pick a larger sample, we might see that we're getting there. So let's take a sample of size 3. 3 random observations chosen. And we get our first mean. Do it again, right, with another sample of size 3. On and on and on to infinity. How do these means distribute? How do all these x bars distribute themselves? Remember, this x bar here is different than this one, right? Because it came from a larger sample, so the value is different. So how do they distribute themselves? Well, if you allow me to actually just sort of say let's put it just right over the top of this one, it would probably start looking something kind of like this. Kind of bell-shaped, kind of a fat bell-shaped curve. And in this particular case, what are the parameters here? Well, we've got a mu, let me change that to white. We have a mu x bar of 1/2, okay, and a sigma squared x bar of, hope you're thinking ahead, 1/12 divided by the sample size. The variance is getting smaller as we're taking a larger sample. That should be somewhat intuitive. The larger sample would mean that your x bar isn't going to be varying as much as you take if you take repeated samples of size n, right? The larger the n, the less variation you have in x bar. So in this particular case, we have a situation where our variance is approaching 0, isn't it? Because we're dividing by an ever-increasing number. But remember, as n is getting larger, what we're seeing here, if you allow me to draw it just on the same graph, we're getting, this is what's happening. As n's going to, sample size 4, sample of size 5 in an infinite number of means, right? A sample of size 6, create an infinite number of means. These means will distribute themselves ever and greater until what you might eventually see in an extreme case would be something like that, where you'd really have to really zoom in and magnify this area up quite a bit to see that what it was really doing was actually forming a very perfectly normal curve. So even though the variance is approaching 0, the curve's getting more perfectly normal in shape. That's the essence of the central limit theorem. No matter what population or what distribution of our original x's, right, the distribution of the x bars approach that. Okay? So that's in essence what it's saying. Now remember, these are theoretical distributions. We're not actually doing these in practice out in the field. Out in the field you're taking a single sample, right? You're taking a sample of, say, I don't know, just say it's size 50. What does that mean? Well, look at it this way. Your sample of size 50, you got some x bar associated with it, didn't you? You calculated what your mean was. That mean is now let me write, and I'll try it. I'll draw a normal curve there. Your mean that you got was now one of the infinite number of means that created this sampling distribution, this frequency distribution of the sample mean. It's now one of the observations. It's now one of the random variables in that distribution. So you know with a sample of size 50, it's generally considered a large sample. I talk about sample sizes in my second video on the central limit theorem, so please view that. This is now considered a large sample. In general, it is. And so the central limit theorem would say, yeah, you've got a reasonably normal curve. It's close enough to be, quote, normal for you to be comfortable with saying that it's a normal curve. Okay? And one other thing. So we know that it's normal. And 2, the sample variance that we got from this sample here, we call that s squared. Not to be confused with sigma squared. Sigma squared was the population variance. The s squared that we got from our sample is a very good approximation to sigma squared. So we can go ahead and say that our sample of size 50 was normal and its variance was a very good approximation to the true variance, and we can invoke what they call, we can invoke this theorem. Okay, and we can now make inferences about the population mean, which we generally don't know. Let me back up here and say something very important. I wrote down the mu and the sigma squared of the population, right? Generally, we don't know what those are, and we want to make some inferences about what they are from the sample. I only wrote these down in advance because just to show you how the numbers are changing. Okay, but in practice, when you're out there and you're taking a sample in an experiment or whatever, you don't know what mu is, and you don't know what sigma squared is, generally speaking. There are cases when you do know it or are very comfortable knowing it. But remember, when your sample is large enough, when we generally have this rule of thumb that says, and I'm not sure if you've been exposed to this or not, generally there's a rule of thumb that says if n is greater than or equal to 30, then we can consider that a large sample and invoke the theorem. And essentially it says that, remember this is what I said over here, your s squared is a good estimator. It's a very good estimator of sigma squared. Even though it is an estimation, we can be reasonably comfortable in saying, okay, we now know what that is. And that allows us to go ahead and use the central limit theorem. We can now then standardize a random variable, use the z distribution, and so forth, if you've gotten that far. I have videos that take care of, or that talk about that sort of stage of the game, z distributions, getting probabilities. Please view those if you wish. Okay, so important just to get the gist of the central limit theorem, what it's saying, and very, very important to understand these frequency distributions of the sample means, or sampling distributions of the mean. They rear their heads over and over and over again. So, important to know. Hope to see you in a future video. Have fun.